Okay, let's use that arithmetic theorem to simplify this abstract expression. So we're going to do some distributions, slowly, carefully. So the A can go in like this, right? And likewise, this A can go in like this. And then I'll take the AB. It'll go in like this. AB. I should maintain my brackets here. Come on. I'll do it like this. AB, C minus AB, D. So I did these distributions. Now, it's important to note, let me just focus on this guy. Okay, the A was hitting the bracket on the left, right? Okay, so it's important. It is essential that this A be on the left of BC and this A be on the left of CD, because we're going to see shortly that in general, if you have a matrix times a matrix, that is usually not going to work the same both ways. Okay, we'll do an example shortly to underline that. But for now, let's continue with this simplification. Minus ACD plus, now I'll move the D in. Now the D here is appearing on the right of that bracket, so it must appear on the right of these two expressions. Now minuses, these distribute as usual. I guess that's not explicitly said in the theorem we just saw, but thankfully it does hold true still. And thankfully, I believe everything is canceling here. Hello, goodbye. Hello, goodbye. Hello, goodbye. So we get 0. So when you write the 0 here, and when you write the 0 in a matrix equation, it is understood that this is not the number 0, but the 0 matrix of the appropriate size. All right. Try this exercise. Try. What are you going to get? Well, you're not going to get the same thing, are you? Okay, AB is 513 minus 2. Just in general, I'm unlikely to get the same thing. Okay. 10 plus 4 is 14. 3, 6 minus 8, negative 2, negative 6. Okay, there's AB. And then BA would be 2, 0, 4, 3, 5, 1, 3, minus 2. 10. Okay, right away. Right there I can see that this 10 doesn't equal this 14. So if this is my question, then the answer is no. So AB in general is not going to equal BA. It could, it's possible. There are cases where it does equal, but not in general. Let me just finish this just for completeness. 29er. 4 minus 6 is minus 2. Okay, way off. I apologize about my 2's. I can't seem to be consistent. I don't know. I'm trying. There we go. Okay, not the same. Okay, more warnings. Okay, so this is violating something you were very used to. Okay, you're used to taking multiplications and changing the order. So just, you're going to do this subconsciously. You're going to make this mistake subconsciously. It's going to take some practice, but try to keep in mind. Okay, some other things to keep in mind. 1, if AB is equal to AC, that does not necessarily mean that I can cancel A. So this is not. Nope. Okay, so this is perhaps unfortunate, you'd say. You just can't cancel that A. Sometimes you can. We'll see later on under what circumstances you can cancel the A. But just in general, you can't cancel the way you would subconsciously like to. And if I have AB equal to the 0 matrix, that does not imply that A is equal to A, or does not imply that A or B is 0 matrix. Okay, let's see if I can dream up some examples here. So example, A times B. If I have 0, if I just choose this carefully, when you're doing counterexamples, you should use 0s and 1s, lots of 0s, and maybe throw a 1 in here and there. There's no need to get complicated. Okay, so this product will equal. Okay, so here we have A times B equal to 0 matrix, but neither of those matrices is itself the 0 matrix. If you want, you can try to think of an example that shows this. Again, just try 2 by 2 matrices, lots of 0s and 1s. Okay, pause and copy this. Now, if AB does equal BA, so this does sometimes happen. Okay, it's just not always true. But if it does happen, then in English we say that A commutes with B. Now, this symbol right here is if and only if. So what that symbol means, a nice way to summarize that phrase. So we're saying that AB is equal to BA if and only if this product equals A squared minus B squared. Okay, this is not a useful way to check whether AB is equal to BA. Okay, I'm doing this example more to talk about if and only if statements, and also I want to talk about this product here. So how am I going to prove this? Well, I should start with, I'm going to start with this guy. So I'm going to start by assuming, so maybe I'll write here, proof. So we'll start with the second statement, and I will show that it implies the first statement and vice versa. So I'm going to do arrows going in one direction first. So what I'm doing, I'm going to assume this is true and see where that leads me. So I'm going to walk down this path and hope to end up here. Okay, so to evaluate this product, what I can do is I can do a distribution. I can think of this as a single entity going like there and also going right there. So I can go A minus B times A. Then plus A minus B times B. That still equals A squared minus B squared. So I did, in this red here, I did a distribution. It's a bit weird looking, but nonetheless is still a distribution. Okay, now the two distributions here are straightforward. We have B and then what? Well, I can subtract, let's say. I can subtract A squared from both sides. If I subtract A squareds from both sides of the equation, then they cancel. If I add B squared to both sides, then they cancel. So I get minus BA plus AB is equal to a 0 matrix. So there you have it. AB does indeed equal BA. All right, that proves one direction. That proves that if this statement is true, then AB must equal BA. But I can see that these arrows, in fact, go both ways. Let's go through one at a time. Now, if I start by assuming this, does that imply that that's true? Well, yeah, because I'm just moving things around. To get from here to here, I just subtract BA from both sides. So that means that this arrow right here goes both ways. Now, to go from here to here, what do? Well, you add A squared to both sides and subtract B squared from both sides. So this arrow goes both ways. To go from here to here, I'm just doing a kind of factoring. I'm reversing my arithmetic I did, which is fine. And likewise, to go from here to here, I'm just reversing that distribution. So these arrows go both ways. So this big monster here shows that this statement is true if and only if this statement is true. Sometimes we say they're logically equivalent.